car of mass 900 kg pulls a trailer of mass 300 kg along a straight horizontal road using a light tow bar which is parallel to the road. Okay, so we've got a trailer which has weight 300 g. We've got a car which has weight 900 g. They both feel tension pulling it away. The horizontal resistance to the motion of the car and the trailer has magnitude 200 and 100 newtons respectively. So car feels 200 newtons resistance and trailer feels 100 newtons resistance. The engine of the car produces a constant horizontal driving force on the car of acceleration on the car of magnitude 1200 newtons. So 1200 pushing it forward. So acceleration is going this way. Part A, show that the acceleration of the car and the trailer is 0.75 meters per second squared. So first thing we have to do is, because we have too many unknowns, we want to ignore tension. So apply Newton's second law horizontally to whole system. Then forces going forward are 1200 plus T, and taking away the forces acting to the left, which is take away T, take away 100, take away 200, must be equal to total mass, which is equal to 1200 kg, so 1200 times acceleration. So let's simplify this. So 1200 take away 100 take away 200 is 900, must be equal to 1200 A, which means A is equal to 900 divided by 1200, which is equal to 0.75 meters per second squared, which is what we wanted. B is find the magnitude of the tension in the tow bar. So to do that, I need to do Newton's second law horizontally on trailer. Then I get T minus 100 must be equal to mass of trailer, which is 300 times acceleration, which is equal to 0.75, which means T must be equal to 300 times 0.75 plus 100, which means T must be equal to 325 newtons. The car is moving along the road when the driver sees a set of traffic lights have turned red. He reduces the force produced by the engine to 0 and applies the brakes. The brakes produce a force on the car of magnitude F newtons, and the car and the trailer decelerate. Given that the resistance to motion are unchanged and the magnitude of the thrust in the tow bar is 100 newtons, find the value of F. So what we need to do is draw a new diagram. So we've got the trailer and we've got the car still. There is no forward motion. They still have the same resistance, which is 200 and 100. They feel the thrust this time. So thrust acts in the opposite direction to tension. So thrust is this way, each feeling 100, is it 100? We said 100 newtons. The car also has a magnitude F making it go back, so F acting this way. So that's it. We don't need to, because when applying Newton's second law horizontally, we don't have to bother with weight. So apply Newton's second law on the whole system. On the whole system, if you apply it only on the trailer, then you can find that acceleration. So we know it's accelerating still, it's moving forwards, so but obviously it's slowing down, so we're expecting A to be negative. So that means applying Newton's second law horizontally on T, then we get minus 100 minus 100, because it's both acting in the opposite direction. So minus 200 will be equal to mass, which is 300 times acceleration. So acceleration is equal to negative 200 over 300, which means acceleration is equal to negative 2 over 3 meters per second squared. So A is equal to negative 2 over 3. And both of them are the same. So we need to find the value of F. So Newton's second law applied horizontally on the car. Then we get negative F, negative take away 200, take away 100, which is all the forces acting to the left, must be equal to mass, which is equal to 900 times negative 2 over 3. They're all negative, so we can change it all to positive. So F plus 200 plus 100 must be equal to 900 divided by 3 is 300, so it's 600. Made a mistake on the first line. So it's negative F take away 200 plus 100, yeah? So plus 100. which means when we change all the signs throughout everything, we get negative 100 here. So that means F take plus 100 must be equal to 600, which means F is equal to 600 take with 100, which is 500 newtons. So that is what we're trying to find out, F. So F is equal to the resistance. So the brakes produce a force on the car of magnitude F. The brakes are producing a force of magnitude 500 newtons. Okay, two particles A and B of mass 4 kg and 3 kg respectively are connected by a light inextensible string which passes over a small, smooth, fixed pulley. The particles are released from rest with the string taut. So we've got a pulley, we've got two particles. A is 4g, so A weighs more. So this is A, so 4g going down, and B is 3 kg, so weight is 3g. A feels tension pulling it up, B feels tension pulling it up. Because A is bigger, A will be moving down, B will be moving up. And we have tension here as well. Okay, it says find the tension in this string. So A is find the tension. So what we do know is if we apply Newton's second law vertically on A, then we know A is moving down, so 4g minus t must be equal to 4 times acceleration, so 4a. So Newton's second law applied vertically on B. B is moving up, so t minus 3g must be equal to 3 times acceleration. So this is equation 1 and equation 2. So if we do equation 1 add 2, one added to 2, then we get the t's disappear. 4g take away 3g is just g, and 4a plus 7a is equal to 4a plus 3a is equal to 7a, which implies a is equal to g over 7 meters per second squared. So that's a, but we didn't want to find acceleration, we wanted to find t. So substituting into either one, so 4g minus t is equal to 4 times g over 7, which implies t is equal to 4g take away 4g over 7, which is equal to 24 over 7g. If you put that into your calculator, you get 33.6 newtons. When A has travelled a distance of 2 meters, it strikes the ground and immediately comes to rest. Find the speed of A when it hits the ground. So if we set up Suva, it travels 2 meters. Initially, the particle is released from rest, so we know it's 0. Okay, we're trying to find the speed when it hits the ground, so this is our final velocity. We know acceleration, we just worked it out, is g over 7. Time, we don't know. So we've got S, U, V, and A, which means V squared is equal to U squared plus 2AS. So V squared is equal to 0 squared plus 2 times g over 7, which means V is equal to square root of 2 times g over 7 just becomes 4g over 7. So V is equal to 2.366431913. So V will be equal to 2.37 meters per second to 2 decimal places. Okay, assuming that B does not hit the pulley, find the greatest height that B reaches above its initial position. Okay, so what we do know is B has already traveled 2 meters when it reaches the point when A hits the ground, yeah? So B, if you think about B is still traveling up. It's already traveled 2 meters. But when it's traveling up, it will eventually come to a point. So it travels up and eventually comes to a point where it stops. So we know that the speed when A hits the speed of A when it hits the ground is equal to speed of B at that point. So the speed of V will be the same, which is 2.37. So initial speed is 2.37. When it reaches its highest, obviously, point and then comes back down, we know the velocity will be equal to 0. So it's going to go from a speed of 2.37 to a speed of 0. So if we set up suvat for B, so for B, okay, we know we're trying to find the distance that it's traveling, so it's question mark. U is obviously the final speed of A, which is equal to 2.3664, blah, blah, blah. I'm using the non-rounded version. The final, its greatest height, we know the final velocity is 0. Now, it's moving up, so the only thing acting on it is gravity. So it's going to be minus 9.8, because obviously it's acting in the opposite direction. So acceleration is minus 9.8, and we don't care about the time. So that means we've got SUVA, which means V squared is equal to U squared plus 2AS. 0 squared is equal to 2.3664, blah, 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 squared, plus 2 times minus 9.8 times S. If I rearrange it, S will be equal to negative 2.3664, blah, 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 squared, over 2 times minus 9.8, which gives me a value of 2/7 meters. So the distance traveled by B, greatest height that B reaches, the greatest height B reaches is the 2 meters that it traveled at the beginning, when at the point where A hits the ground, plus the 2/7 meters that it does afterwards until it gets to its greatest height, which means it's the same thing as 2 2/7 meters. Two particles A and B of mass 0.4 kg and 0.8 kg respectively are connected by a light inextensible string. Particle A lies on a rough horizontal table 4.5 meters from a small smooth pulley which is fixed at the end of a table. The string passes over a pulley and the B hangs freely with the string taut 0.5 meters above the horizontal ground. A frictional force of magnitude 0.08 G opposes the motion of the particle A. The system is released from rest. So we've got a table, we've got a pulley, string and string. We've got particle B, and particle B, it weighs 0.8 kg, so the mass weight is 0.8 G. And if we have the ground, it is, the distance from the ground is 0.5 meters. So 0.5 meters. I'm just going to do it in different color so we can see the different things. We've got a particle A, or A here, okay, which has weight 0.4 G. Okay, and it also has a frictional force in the opposite, acting in the opposite direction, which is 0.08 G. Okay, and obviously A feels tension, the pulley feels tension, we have tension here and tension, and the only other thing is we know that A is also 4.5 meters away from the pulley. Okay, when it's released, acceleration will be this way, acceleration will be that way. So find the acceleration of the system. So Newton's second law applied vertically on B, I get 0.8 G minus T must be equal to 0.8 times acceleration, which is equation 1. Equation 2 from Newton's second law applied horizontally on A, I get the tension minus 0.08 G must be equal to 0.4 times acceleration. So this is 2. Okay, if I do 1 add 2, I end up getting, the t's cancel out, so all I get is 0.8 G taken by 0hg, which is equal to 0.72g, must be equal to 1.2a when we add them together. So a must be equal to 0.72g over 1.2, which is equal to 0.6g meters per second squared. The time taken, part B, the time taken for B to reach the ground. Okay, so for B, let's do that. So reaching the ground for B is travels 0.5 meters. Start initially from rest. We don't know the final velocity. We know acceleration is 0.6g. We're trying to find the time it takes. So that means we've got S, U, A, and T. So S is equal to UT plus half AT squared. So 0.5 is equal to 0 times T plus half times 0.6g times T squared. So that will just cancel out because it's just 0. So that means when I rearrange it, T will be equal to square root of 0.5 divided by 0.5 times 0.6g. So T works out to be 0.412393 blah blah blah, which works out to be to 2 decimal places 0.41 seconds. See the total distance traveled by A before it first comes to rest. Okay, so we know A has traveled 0.5. So when A, for part C, when B hits ground, A has already traveled 0.5 meters. Okay, so what we need to do is, first of all, we need to find out the velocity at which B hits the ground. So velocity for B, so if we want to find out velocity at which it hits the ground, we set up SUVAT. We know the distance traveled is 0.5, initial speed was 0. We need trying to find the final speed, which is v. Acceleration is 0.6g. Time we do know is 0.41 second, but because it's one that we worked out, let's use S, U, V, and A to find out what V is. So V squared is equal to U squared plus 2AS, which means V will be equal to square root of 0 squared plus 2 times 0.6g times 0.5, which works out to be V is equal to 2.42487 blah blah blah, which means V is equal to 2.42 meters per second. So that means A is traveling hits the ground at 2.42 meters per second. So when so let's go here. So A is traveling at 2.42 meters per second when B hits the ground. After B hits ground, the string goes slack. So A is traveling and there is no tension. Therefore, no tension in string. So which means the only force acting on A is pushing it backwards by 0.08g, which means if I apply Newton's second law horizontally to A, then that means negative 0.08g, because there is no tension on the string because it's gone slack, will be equal to mass, which is equal to 0.4 times acceleration. So acceleration has changed because B has hit the ground. So it's going to be negative 0.08g divided by 0.4, which works out to be negative 0.2 times g. So this is the new acceleration. So now because the A will travel, so A is traveling from velocity of 2.42 to the time it comes to rest, which is v is equal to 0. So initial speed is 2.42, and when it comes to stop, it will be velocity 0. Then for A, if we set up a suvat, we're trying to find the distance traveled. We know the speed at the initially, when after it's traveled 0.5 meters, is 2.42487, blah, blah, blah. The final velocity is 0. The acceleration is negative 0.2 g. We don't care about the time. So we've got SUVA, which means v squared is equal to u squared plus 2as, which means 0 squared is equal to 2.4248 blah, blah, blah squared plus 2 times negative 0.2 times g times s, which means if I rearrange it, s will be equal to negative 2.4248 blah, blah, blah squared divided by 2 times negative 0.2 g. If I put that into my calculator, s comes out as 1.5 meters. Therefore, distance traveled by A distance traveled by A is equal to the 0.5 meters initially plus 1.5 that I've just worked out now, which works out to be 2 meters. Next question. Two particles A and B have mass m, kg, and 3 kg respectively, where m is greater than 3. So if m is greater than 3, it means it's traveling this way, and B is going up. Okay, so B, the weight of B is 3g, and this is mg. There's tension here, tension here, tension there, tension there. Okay, the particles are connected by a light inextensible string which passes over a smooth pulley. Initially, A is 2.5 meters above horizontal ground. The particles are released from rest with the string taut and the hanging parts of the string vertical, as shown in the figure. After A has been descending for 1.525 seconds, it strikes the ground. Particle A reaches the ground before B has reached the pulley. Show that the acceleration of B as it ascends is 3.2 meters per second. So we want to work out acceleration. So acceleration of A, because it's an extensible string, acceleration of A is equal to acceleration of B. Therefore, if we look at, because we know enough information about A, so if we set up suvat for A, then that means we can use one of the equation of motions to solve to find A. So we know A has traveled 2.5 meters when he hits the ground. So A is 2.5. Initial speed is 0. We don't know the final speed. We're trying to find that acceleration, and we know that it hits the ground 1.25 seconds later. So what we have is S, U, A, and T. So S is equal to UT plus half AT squared. That's the equation that we're using. So 2.5 is equal to 0 times 1.25 plus half A times 1.25 squared. So that means if I rearrange it, A will be equal to 2.5 divided by half times 1.25 squared, which gives me acceleration of 3.2 meters per second squared, which is what I wanted. Okay, part B, find the tension in the strings as A descends. Okay, because there's too many unknowns in A, I will apply Newton's second law to B. So Newton's second law applied vertically to B. Then that means I know the T minus 3g must be equal to mass, which is 3 times acceleration, which is 3.2. So tension will be equal to 3 times 3.2 plus 3g, which means tension will be equal to, if we put this into our calculator with g is equal to 9.8, tension is equal to 39 newtons. part C, show that m is equal to 65/11. So let's apply Newton's second law vertically on A now. And what we do know is mg minus tension must be equal to mass times acceleration. So mass times 3.2. Now what we do know is tension is 39. So mg minus 39, so from part B, must be equal to m times 3.2, which means 39, if I rearrange it, must be equal to, if I take mg to the other side, it must be mg minus m times 3.2. If I factorize it out, 39 must be equal to m times g minus 3.2, which means m must be equal to 39 over g minus 3.2, which works out to be 65/11 kg. State how you have used the information that the string is inextensible. Inextensible means acceleration is the same on either side of the pulley. Okay, so last part is when A strikes the ground, it does not rebound and the string becomes slack. Particle B then moves freely under gravity without reaching the pulley until the string becomes taut again. Find the time between the instant when A strikes the ground and the instant when the string becomes taut again. So what happens to B after A hits the ground, B will go up and then come back to the same spot again. So B will go up and come back to the same spot. So B will go up to its maximum height and then come back down. So what we need to think about is we need to find the velocity after A hits the ground. We need to find the velocity. So at this point, when A hits ground, we know that acceleration for after that point, acceleration will be equal to, it will be acting with gravity. So it will be being pulled down by gravity. So acceleration will be equal to minus 9.8. And then we know at this point, at the maximum point, velocity is equal to 0. So if we can find the time it takes to travel from when the velocity, so from the point that A hits the ground to the maximum height, then if we double it, because because acceleration is constant throughout the whole journey, then we have to double it to get the time it takes to come back for the string to be taut again. So the first thing we need to do is find out the velocity when A hits the ground. So for B, if we're setting up a suvat, so when A hits the ground, it's still accelerating with the same speed as before, so the same acceleration as before, which is 3.2. So it's before, the acceleration is 3.2 at this stage. So the distance traveled by B would be 2.5 because it's the same distance as A, 2.5. Initial speed is 0. We're trying to find the final speed. We don't care what T is. So we've got S, U, V, and A. So if we want V squared is equal to U squared plus 2AS, which means V squared is equal to 0 squared plus 2 times 2.5 times 3.2. So V will be equal to square root of 2 times 2.5 times 3.2, which works out to be 4 meters per second. So when A hits the ground, B is traveling at 4 meters per second. So this is equal to 4 meters per second. Now we need to look at the journey from, so for B, journey from when A hits the ground to B reaching maximum height. So if we set up a suvat for that, S-U-V-A-N-T, then we know, you don't know the distance traveled, we know the We know the initial velocity when A hits the ground is 4 meters per second. When B is at its maximum, velocity is equal to 0 because it's going to change direction. Acceleration is gravity is pulling it down, so it's going to be minus 9.8. And the time is what we're trying to figure out. So we've got U, V, A, and T. So that means V is equal to U plus AT. So 0 is equal to 4 plus minus 9.8 T, which means T is equal to negative 4 over negative 9.8, which works out to be 20 over 49 seconds. So that means slack 2 towards, sorry, it will be double that. So it will be double that because acceleration, since acceleration is minus 9.8 throughout, then the time is equal to 2 times 20 over 49, which is equal to 40 over 49. Oops, 40 over 49 seconds. Okay, last question I'll go through. A box P of mass 2.5 kg rests on a rough horizontal table and is attached to one end of a light inextensible string. So tension here, tension there, tension here, tension there. So this will be 1.5 G, 2.5 G. The string passes over a small smooth pulley fixed at the edge of a table. The other end of the string is attached to a sphere Q of mass 1.5 kg, which hangs freely below the pulley. The magnitude of the friction force between P and the table is K newtons. So K going backwards. The system is released from rest with a string taut. After release, Q descends a distance of 0.8 meters in 0.75 seconds. So modeling P and Q as particles, calculate the acceleration of Q. A, part 1. So if we set up a that for Q, so we know it's descended 0.8 meters with initial speed of 0. We don't know a final speed. We're trying to work out the acceleration, and we know the time is 0.75 seconds to travel this distance. We've got S, U, A, and T. So S is equal to UT plus half AT squared. 0.8 is equal to 0 times 0.75 plus half times A times 0.75 squared. Which means if I rearrange it, A will be equal to 0.8 divided by half times 0.75 squared, which means A is equal to 2.84 recurring meters per second squared, which implies A is equal to 2.84 meters per second squared. Part 2, show that the tension in the string is 10.4 newtons to 3 significant figures. So part 2, Newton's second law. Because we have an unknown in K, another unknown involved, we might as well do it. Apply Newton's second law vertically to Q. Then that means we have 1.5 G minus tension must be equal to 1.5 times acceleration, which is 2.84 recurring. So if I rearrange it, I get 1.5 G, take away 1.5 times 2.84 recurring, which means tension works out to be 10.43 recurring. When rounded, tension is 10.4 newtons to 3 significant figures. Find the value of K, so part 3. Newton's second law applied horizontally to P. Then we have T minus K must be equal to mass, which is 2.5 times acceleration, which is 2.84 recurring. But we know tension is already 10.43 recurring. So 10.43 recurring minus K must be equal to 2.5 times 2.84 recurring, which means K must be equal to 10.43 recurring minus 2.5 times 2.84 recurring, K is equal to 3.32 recurring, which means K is equal to 3.3 newtons to two significant figures. That's A done. B is state how in your calculation you have used this information that the string is inextensible. It means acceleration is the same throughout the string and on either side of the pulley.